Okay, I'd like to finish off Module 15 about carbocations by discussing one weird thing that happens with carbocations. So I've already talked about the fact that carbocations are very high energy reaction intermediates. Because of that fact, it turns out, because they're so unstable and desperate to relieve some of the strain of having an incomplete octet, sometimes they'll do things that we might not have predicted. So here's an example of a reaction that you could probably predict the result of. So I'm reacting an alkene with an acid, in this case HCl, and you'll see this reaction more explicitly in the next module. But if you had to take a guess, we've seen that we can form carbocations by reacting alkenes with acids. So you might guess that the first thing that will happen is the alkene is going to grab a proton from the acid. That gives me a choice. I could either make a carbocation at the end, or I could make a carbocation on that second carbon. And based on our prior discussion, we would say that a primary carbocation is going to be much more unstable than a secondary carbocation. So the primary carbocation would be slower to form. So we'll only really observe the secondary carbocation. And then if you had to ask yourself, if you're predicting the product of the reaction overall, now that I have a carbocation, that seems like it's going to be desperate for electrons. I have just released a Cl minus ion into solution when I grab the proton away from HCl. That seems like a good candidate to go ahead and attack the carbocation. And give us this product here. Turns out that's not the observed result. Even though that would be a logical guess, the actual result is that we get a compound that looks like this. And to emphasize the point, I'm going to number the carbons in my starting material and product. So 1, 2, 3, 4, 5, and 6. So I expected my carbon chain to stay exactly like it was. Turns out what happens instead is I make a carbon chain that looks like this: 1, 2, 3, 4, 5, and 6, with my chlorine now bonded to carbon 2 instead. So this was something that chemists observed and then had to try and come up with an explanation for. So let's see if we can come up with an explanation. We get an unexpected product. Let's examine our mechanism. In the first step of the mechanism, we predicted that we would form a secondary carbocation. I'm going to stick with that same first step. Then I'm going to ask myself, why is it that we said we would make a secondary carbocation instead of a primary carbocation? And the answer was hyperconjugation. We know that the secondary carbocation is stabilized by hyperconjugation. So what that means, to reiterate, is that I have my carbocation. It's planar. It's got an empty p orbital. It's got a hydrogen here, a methyl group over there. That's carbon 4. Just for perspective, this is carbon 3. This is carbon 4. Over here, I had carbon 2, which is bonded to carbons 1, 5, and 6. It's tetrahedral, so one of those should be coming out of the page, one of them should be going into the page, one of them should be in the plane of the page. So I'm going to draw it like this. So those are my carbons. Now remember, we said hyperconjugation was donation from a neighboring sigma bond. So for instance, here I have a sigma CC bond, and it can be donating into the empty p orbital. That's hyperconjugation. What if that hyperconjugation gets taken to the extreme? And instead of just donating a little bit of electron density, the electrons actually slide over and bond to carbon 3 instead. How would that change my picture? So if I took hyperconjugation to the extreme, now carbon 3 is going to become a tertiary carbon. So carbon 3 will now have carbon 6 bonded to it, still be bonded to 4. Carbon 2 now is going to be the one left with an incomplete octet. Where this is now 1 and this is 5. So that would be what we call hyperconjugation taken all the way to the extreme, where we're donating the electrons completely. Notice now our carbon chain has changed. We call this an alkyl shift. And really an alkyl shift is just hyperconjugation to the extreme. What would that look like in terms of curved arrows? What it would look like in terms of curved arrows is I'm going to take the sigma bond between 2 and 6, and I'm going to draw an arrow from that to the carbocation. And now the product of that step will look like this. 1, 2, 3, 4. Now this is 6 and this is 5. I took electrons away from carbon 2, so carbon 2 is now the carbocation. So this is an alkyl shift, also known as a carbocation rearrangement, and it really causes a change in the carbon-carbon chain of the molecule. Now, you might ask yourself, why would this happen? Well, notice now that the carbocation has moved from carbon 3 to carbon 2. It went from being a secondary carbocation to being a tertiary carbocation. We know that a tertiary carbocation is less unstable because it has more opportunity for hyperconjugation. Now there can be hyperconjugation from carbon 3, from carbon 1, from carbon 5. So that tertiary carbocation is less unstable. So that's the driving force for this rearrangement. After that rearrangement, the carbocation is as stable as it's going to get, and it's going to wait there until a nucleophile can come and bond to it, in this case, the chloride ion. And that will make this product. Students often ask, well, why doesn't the chloride attack before the alkyl shift happens? And that's a great question. the thing about intramolecular reactions, so reactions that occur within a molecule, is that because the reactant orbitals are already lined up, they're already next to each other, those reactions tend to be faster than reactions between molecules, which rely the two molecules to bump into each other in the right orientation for the reaction to happen, which, because they're moving randomly, usually is going to take longer than the intramolecular reaction. So when these alkyl shifts are favorable, as this one is, then they're likely to occur before any intermolecular reaction can happen. The pattern to look for here, notice we made a secondary carbocation, and then the carbon next door, if I had to characterize carbon 2, it's bonded to 4 other carbons. We call this a quaternary carbon. Bonded to 1 other carbon is a primary, 2 is a secondary, bonded to 3 other carbons is tertiary. This carbon 2 here is a quaternary carbon because it's bonded to 4 other carbons. So the pattern to look for here is that we have a secondary carbocation next to a quaternary carbon. This would work with a primary carbocation too. If it's next to a quaternary carbon, then that alkyl shift will be favorable. And so we should expect to see that. So that's case 1. Secondary carbocation next to a quaternary carbon. So an alkyl shift will happen when there's a driving force that will make the carbocation less unstable. All right. So that was one case. Another case I want to show you that's also fun. Here, I start with a 4-membered ring. And you may remember from Module 7 that 4-membered rings have what we call ring strain. The orbitals don't align the way they'd like to because the bond angles are too small. That results in 4-membered rings being less stable than they otherwise would be. So if I take this alkene and I react it with HBr, again, you might expect to follow a pathway where you make the secondary carbocation, because you have a choice between primary and secondary. You might expect, okay, I'm going to form the secondary carbocation, and then because the carbocation is so reactive, it's going to react with Br minus and make this product here. Well, what I'm telling you with this big red X is that this product is not actually observed. So this doesn't actually happen that way. So again, we need to come up with an explanation. I am going to stick with that same first step. I'll form a secondary carbocation. I'm going to number my carbons again to make my life easier. This is especially important when we are dealing with rings and the size of the ring is changing. I'm going to guess that in the product, this is still carbon 1 and still carbon 2 and still carbon 3, 4, 5, and 6. But what I'm noticing now is that in my product, instead of having a bond from 6 to 3, I now have a bond from 6 to 2. So when I have my high energy intermediate, this carbocation here, I ask myself, how can I break the bond from 3 to 6 and make a bond from 6 to 2? Well, again, this is going to be an alkyl shift where these electrons slide over. And in this step, I break the 3 to 6 bond and I form a 6 to 2 bond. When I do that, now, instead of having a 4-membered ring, I'll have a 5-membered ring. And this is 6, 5, 4, 3, 2, and then carbon 1 would be bonded to carbon 2. And I ask myself, who did I take electrons away from in that step? Well, carbon 3 had the bond and it no longer does. So I took electrons away from carbon 3. Carbon 3, notice, had one hydrogen on it. It still has one hydrogen, but it only has 3 bonds total now. So it has a carbocation. And if I then attack that carbocation with a bromide ion, I will make the observed product. So you might ask yourself, well, what's the driving force for this step? Well, here I had a secondary carbocation. I still have a secondary carbocation after that alkyl shift. So that's not the driving force in this case. But what I did do is I went from a 4-membered ring to a 5-membered ring. Remember, a 4-membered ring has lots of strain, ring strain. And I went to a 5-membered ring. A 4-membered ring has lots of ring strain, but a 5-membered ring has very little ring strain. So the driving force here is that we relieve some ring strain. So this second situation, when you have a carbocation next to a strained 4-membered ring, it will often do this kind of alkyl shift where it increases the size of the ring, opens it up, and that relieves ring strain. Okay, so those are 2 kinds of alkyl shifts that you'll encounter in the skill builder and the skill checkers. There are others, but I'm not likely to show them to you in this class, but you may see them in future classes. So that wraps up Module 15 on carbocations. And after that, you're ready to dive into more reactions of alkenes.